when stability started, depending on algorithms. It did not arrive as dependence. It arrived as relief. Systems stopped failing unexpectedly. Crises became manageable. Instability softened into something that felt predictable. The change was welcomed precisely because the old way of maintaining balance had been exhausting, unreliable, and visibly imperfect. What replaced it was smooth, fast, and invisible, which made it feel like an upgrade rather than a substitution. To understand why this matters now, we need to recall how stability once worked. Balance emerged from buffers, slack, and human judgment. When conditions shifted, people adapted. Errors were corrected through experience and negotiation. Stability was not a state that was achieved once and maintained forever. It was an ongoing act of adjustment, a conversation between human awareness and environmental change that required constant participation. That model strained as systems accelerated. Human response became too slow. Complexity outpaced intuition. Algorithms stepped in to manage flows, allocate resources, and smooth volatility. Stability improved immediately. The transition felt natural because the algorithms delivered exactly what humans had been struggling to provide: fast, consistent, reliable balance across systems too complex for any individual or committee to monitor. At first, this felt like progress. Power grids balanced themselves. Markets adjusted automatically. Logistics rerouted around disruption. Algorithms absorbed shock faster than any committee could. The results were measurable and impressive, and the contrast with the old model, which had been slow, contentious, and prone to human error, made the new approach seem not just better, but inevitable. But something subtle changed. Stability stopped being emergent. It became engineered. Balance no longer came from resilience, but from constant calculation. The difference was profound, even if it was invisible. Emergent stability can absorb surprises because it arises from diverse, loosely coupled responses. Engineered stability depends on the accuracy of the models that produce it, and models are only as good as the assumptions they encode. The earliest warning signs were invisible. Human understanding faded as reliance grew. Fewer people knew how systems worked without algorithmic support. Manual intervention became rare, then unfamiliar. The knowledge that had once sustained stability migrated from human minds into code, and as it did, the ability to verify, challenge, or replace that code diminished. Stability held as long as algorithms functioned, and because they worked so well, questioning them felt unnecessary. The success of automation silenced the doubts that might have prompted preparation for its failure. But dependence crept in quietly. What once assisted judgment began replacing it. Stability no longer depended on people making choices. It depended on systems making them continuously. And once stability depends on algorithms, the question is no longer how stable the system feels. It is what happens when the systems that provide that stability are no longer there. As algorithms took over stabilizing roles, humans adapted around their reliability. Procedures assumed constant optimization. Training focused on exception handling rather than understanding fundamentals. Stability became something delivered, not maintained. The human role shrank from active participant to passive recipient. From someone who created balance to someone who consumed it. The conflict emerged when algorithms began interacting with one another. Stabilizing one system introduced volatility into another. Local balance produced global tension. Algorithms optimized their domains without awareness of the whole. Each algorithm pursued its own objective with precision, but precision applied independently across interconnected systems is not the same as coordination. This created hidden coupling. Systems appeared calm until stress exceeded modeled boundaries. When conditions fell outside trained scenarios, responses were fast but misaligned. Stability gave way suddenly, not gradually. The failure mode was characteristic of algorithmic dependence, not slow degradation, but abrupt discontinuity, a snap from apparent order to genuine chaos. Engineers noticed a dangerous pattern. Algorithms excel at maintaining equilibrium within known ranges. They struggle with novelty. When unprecedented events occurred, automated responses amplified disruption instead of containing it. The algorithms did not know they were confused. They responded with the same speed and confidence to situations they understood and situations they did not. And the inability to distinguish between the two was perhaps the most dangerous feature of the entire arrangement. The emotional tension rose as people realized how thin the margin had become. Manual backups existed on paper, but not in practice. Skills had atrophied. Confidence in human intervention faded. The generation of operators who had maintained stability without algorithms was retiring, and the generation that replaced them had never known a world where stability required their active participation. Stability was no longer layered. It was singular. If algorithms worked, everything worked. If they failed, nothing compensated. The redundancy that had once characterized robust systems, multiple independent sources of balance, had been consolidated into a single mechanism that was efficient but solitary. This revealed the trade-off that had been quietly accepted. Smoothness replaced robustness. Efficiency replaced slack. Stability became brittle. The system was optimized for the expected and defenseless against the unexpected, a condition that felt like strength right up until the moment it revealed itself as vulnerability. When stability started depending on algorithms, it did not remove risk. It concentrated it. And concentrated risk does not announce itself until the moment it breaks. The conflict reached its peak when algorithmic stability faced conditions it had never learned from. Shocks arrived outside historical patterns. Inputs broke assumptions. Models extrapolated where they should have paused. The algorithms continued to act with full conviction in situations where the correct response would have been uncertainty, but they had no mechanism for expressing doubt. Automated responses triggered each other. One system corrected aggressively. Another interpreted that correction as a new threat. Feedback loops tightened. Stability mechanisms amplified instability. The cascade was fast and bewildering because it moved at machine speed through pathways that human operators could not trace in real time. Humans were slow to respond, not because they were absent, but because they were unprepared. Oversight existed, but understanding did not. Intervening required insight that had faded through disuse. The manual override was technically available, but practically useless, because the people tasked with using it no longer possessed the situational awareness that effective intervention demands. The emotional peak arrived with a stark realization. Stability had not been removed from human hands. It had been outsourced beyond human reflex. When speed matters more than comprehension, control becomes symbolic. The control room still existed. The dashboard still glowed. But the gap between what was being displayed and what could be meaningfully acted upon had widened into an abyss. Engineers recognized the trap. Algorithms are excellent at maintaining balance they have seen before. They are poor at imagining what they have not. Novelty is their blind spot. And in a world that continues to produce novel conditions, a stability mechanism that cannot handle novelty is not a stability mechanism at all. It is a fair-weather friend. When stability depends on algorithms alone, surprise becomes catastrophic. There is no gradual warning, only sudden mismatch between reality and expectation. The systems did not fail because they were weak. They failed because they were too precise for a world that still changes. And in that precision, humanity discovered how fragile automated calm can be. The resolution did not come from abandoning algorithms. It came from restoring balance between automation and human judgment. Stability could not remain a single point of failure. The answer was not to retreat from algorithmic assistance, but to refuse to let it become the only source of balance. Engineers reintroduced slack. Manual pathways were kept alive through practice, not paperwork. Algorithms were designed to defer, not dominate, when uncertainty crossed human-defined thresholds. Stability slowed slightly, but resilience returned. The systems became less impressive in their smoothness, but more trustworthy in their honesty, signaling strain rather than concealing it. This marked a shift in philosophy. Stability was no longer treated as constant smoothness. It was treated as recoverability. Systems were allowed to wobble so they would not shatter. The new standard accepted visible imperfection as the price of genuine resilience, a trade-off that would have seemed absurd in the era of algorithmic confidence, but now appeared self-evident. The deeper lesson was clear. Algorithms are powerful stabilizers, but they do not understand meaning, context, or surprise. Humans do. Removing people from stability removes the ability to reinterpret the situation when the world changes. The qualities that make human judgment slow, its reliance on context, its sensitivity to ambiguity, its capacity for doubt, are precisely the qualities that make it indispensable when the world departs from what models expect. When stability started depending on algorithms, the danger was not automation itself. It was forgetting how to stand without it. The future will belong to systems that balance speed with understanding and precision with humility. Because true stability is not the absence of disruption. It is the ability to adapt when disruption arrives. Subscribe to join the journey.